Welcome to this session. This session we are going to discuss about partial derivatives of implicit functions by Jacobian method. So given f1 of x, y, u, v equals to 0, and f2 of x, y, u, v equal to 0, so this case 1, then to define partial u, partial x, you get negative of partial f1, f2, partial x v divided by partial f1, f2 over partial u v. So which is the same thing can be written as negative partial f1, f2, partial x v, partial f1, f2, and then partial u v. So you can prove that one by writing the chain rule derivative of f1 with respect to x, and then f2 with respect to x, and then solving for partial u, partial x. And then second formula, partial v, partial x is given by, now this one is positive, partial f1, f2, partial x u, and then partial f1, f2 over partial v u, which can just be written as the Jacobian of f1, f2 with respect to x and u, Jacobian of f1, f2 with respect to v and u. Remember, these results are obtained by using chain rule to find partial f1, partial x, and partial f2, partial y, and making partial u, partial x, and partial v, partial x the subject. So case 2, if f1 now is given in terms of x, y, z, u, v, w equals to 0, f2, x, y, z, u, v, w equals to 0, and f3, x, y, z, u, v, w equals to 0, then to define partial x, partial u, you get minus partial f1, f2, f3, partial u, y, z, and then Jacobian f1, f2, f3 with respect to x, y, z, and so on. So just taking the same format as what you have done in case 1. So what you have to note here NB, that first we write the Jacobian in the denominator, and then we write the Jacobian in the numerator by replacing x by u. So that's what we do to get partial x, partial u. As an example, use Jacobians to find partial u, partial x, if this would be u squared plus x v squared is given by x squared minus xy is equals to 0, and u squared plus x y v plus v squared equals to 0. Now, these are case of two functions. So solution will let this one to be f1 and let this one to be f2. So let f1 be given by u squared plus x v squared minus xy, and f2 to be given by u squared plus xy v plus v squared. Then the Jacobian of f1, f2 with respect to u v will be partial f1 partial u partial f1 partial v partial f2 partial u partial f2 partial v equals to, this will give us 2u, and then we have 2xv, then we have 2u, then we have xy plus 2v. And when we evaluate this determinant, you get 2u xy plus 4u v minus 4u xv. Expanding this, we get that value. Next, the Jacobian of f1, f2 with respect to xv is the determinant partial f1 partial x partial f1 partial v, and then partial f2 partial x partial f2 partial v, and when you work out this, you get v squared minus y 2xv, and then y v, and this would be xy plus 2v. This, when you work out, you get negative x y v squared plus 2v power 3 minus xy squared minus 2yv. Now, by definition, partial u partial x is negative. The Jacobian of f1, f2 with respect to x, y divided by Jacobian of f1, f2 with respect to u, v, and this will be x, y, v squared minus 2v cubed plus x, y squared plus 2yv divided by 2uxy plus 4uv minus 2xuv. And that is the solution to that problem. Thank you.